Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence. I'm excited to dive into today's topic. We're going to be discussing a paper exploring how large language models perform on USA Math Olympiad problems, which I think is a fascinating test of true understanding versus just pattern recognition. What are your initial thoughts on using something like the Math Olympiad as a benchmark?
I think it's brilliant. It's a really clever way to stress test these LMs and see if they're actually reasoning or just regurgitating patterns they've seen in their training data. These aren't your everyday math problems. They require abstract thought, spatial reasoning, and often coming up with novel solutions. It's a much better benchmark than, say, just asking them to solve quadratic equations.
I agree it's a good challenge, but I'm inherently skeptical of relying solely on deep learning for these kinds of tasks. My initial thought is that these models will likely struggle because the Olympiad problems demand a level of symbolic manipulation and logical deduction that deep learning, in its current form, just isn't equipped to handle. It's like using a hammer to screw in a bolt. You might get it done, but it's not the right tool.
I'm also a bit skeptical, but for a slightly different reason. I think the problem isn't necessarily deep learning itself, but the way we're using it. It feels like we're throwing massive amounts of data at these models, hoping that intelligence will somehow emerge. But intelligence will somehow emerge. But intelligence, especially mathematical intelligence, is about more than just pattern recognition. It's about understanding relationships, translating between different representations, geometric, algebraic, symbolic, and reasoning spatiotemporally. And I suspect that current models are really weak in that area.
That's a really interesting point, Donald, about spatiotemporal reasoning. It makes me think about how humans often visualize these problems, rotating shapes in their minds or drawing diagrams to understand relationships. Do you think the lack of that kind of embodied cognition is a fundamental limitation for these models?
Absolutely. I think that's a huge piece of it. We, as humans, don't just see the equations, we see the geometry behind them. We understand how things move and relate to each other in space and time. And I think if a model could seamlessly switch between different coordinate systems and apply them to the problems, it might unlock a hidden structure that could lead to a different understanding of the solution. If you're missing that core algorithm to translate between different coordinate representations, it's never going to get there. Current deep learning is too brute force.
I can see that, but the recent advances in deep learning, especially with transformers, have been pretty remarkable. I mean, these models are learning complex relationships and generating coherent text, translating languages, and even writing code. Isn't it possible that with enough data and a sufficiently large model, they could eventually learn to reason mathematically as well?
I think that's a dangerous assumption. Just because a model can generate plausible sounding text doesn't mean it understands the underlying concepts. It's really good at mimicking patterns, but it doesn't possess actual understanding. It's a sophisticated parrot, not a mathematician. I think that's why we need to explore neuro-symbolic approaches that can integrate symbolic knowledge and logical reasoning into these models.
Can you elaborate a bit on what a neuro-symbolic approach would look like in practice, Sarah? How would it differ from the current deep learning paradigm?
Sure. So instead of just relying on massive amounts of data to train a neural network, you would explicitly encode mathematical knowledge and logical rules into the system. For example, you could use a symbolic reasoning engine to perform deductions and inferences, and then use a neural network to learn how to apply those rules in different contexts. It's about combining the strengths of both approaches, the pattern recognition abilities of deep learning with the reasoning capabilities of symbolic AI.
That sounds interesting. So, like, having a system that can both recognize a pattern in a geometric figure and apply the relevant theorems to prove a property of that figure.
Exactly. You'd have the neural network identify relevant features and patterns, and then the symbolic engine would use those features to construct a logical proof. It's about building a system that actually understands the underlying mathematical principles rather than just memorizing solutions.
Yeah, I agree that pure deep learning is likely insufficient. I also agree with this neuro-symbolic approach. I think for these Olympiad problems, a key thing is probably the ability to translate between different spatial representations in particular. So the neural network is the representation learning part, and then the symbolic engine is reasoning. But if you don't have the neural network being able to do that part, no matter how good your engine is, it's just not going to work.
I see what you're saying. It's about having a more structured and interpretable representation of knowledge. But isn't it possible that deep learning models are already learning some kind of internal representation of these mathematical concepts, even if we don't fully understand it? I mean, they are able to solve some pretty complex problems.
They can appear to solve complex problems, but I think it's often a superficial understanding. They might be able to find correlations between problem statements and solutions, but they don't necessarily understand the underlying logic. That's why they're so easily fooled by adversarial examples or problems that are slightly different from what they've seen before. They are also not good at interpolation. They work better in areas that are trained than untrained. It is an indication of lack of true understanding.
That brings up an interesting point about adversarial examples. If these models are just learning patterns, then they should be vulnerable to carefully crafted inputs that exploit those patterns. I wonder if the paper explores that aspect at all.
I think it implicitly does. Because these Olympiad problems are designed by humans to be resistant to pattern recognition, these examples could be thought of as adversarial examples.
I think there are more fundamental reasons for that adversarial nature. The problems require the translation and understanding of spatial relationships. The adversarial examples are designed to trick people by exploiting the limitations in our cognitive ability to understand that. I think, therefore, that a truly good solution to that will be for the AI to have supercognitive abilities.
So, stepping back for a moment, what are the broader implications of this research? If LLMs struggle with these kinds of problems, what does that tell us about the current state of AI and its potential for achieving true general intelligence?
I think it's a wake-up call. It shows that we're not as close to AGI as some people might think. Deep learning has made tremendous progress, but it's not a magic bullet. We need to explore other approaches, like neuro-symbolic AI, and focus on building systems that can truly reason and understand the world.
I completely agree. I think it highlights the need for a more nuanced and holistic approach to AI development. We can't just rely on brute force methods and massive datasets. We need to incorporate cognitive principles, symbolic knowledge, and logical reasoning into our models.
Right. It's about finding the right algorithm, not just throwing more data at the problem. We need to focus on building AI systems that can understand and translate between different representations, spatial, temporal, symbolic, and that can reason about the world in a more human-like way. It's about building AI that can actually think, not just mimic thinking.
But isn't it possible that the limitations we're seeing are just a matter of scale? Maybe we just need even larger models and even more data to overcome these challenges. I mean, these models are constantly improving, and they're already capable of doing things that were unimaginable just a few years ago.
I think that's wishful thinking. There are fundamental limitations to the deep learning approach that won't be solved by simply scaling up the models. It's like trying to build a skyscraper on a foundation of sand. No matter how tall you build it, it's eventually going to collapse. We need to build a more solid foundation based on cognitive principles and symbolic reasoning. The challenge is not just to get the machine to produce the correct answer, but to get it to do so in a way that is analogous to the way humans approach the problem. In other words, can we get the machine to think like a human mathematician?
I think it is more about what Sarah said. The core algorithm has to change. In the example of these problems, you need translation. It's not about data. You can have all the data you want. But if the core of the algorithm can't translate, the quality of the data doesn't matter. No amount of data will change that.
So, let's shift gears a bit and think about future research directions. Based on this discussion, what are some of the most promising avenues for exploring the path to more intelligent machines?
I think one promising direction is to continue exploring different neural network architectures, especially those that are better at handling spatial relationships and abstract reasoning. Things like graph neural networks or attention mechanisms might be particularly useful. And of course, we need to keep pushing the boundaries of scale, training larger and larger models on ever-increasing datasets.
I think we need to focus on developing more sophisticated neuro-symbolic algorithms that can integrate symbolic knowledge and logical reasoning into deep learning models. This could involve using symbolic reasoning engines to guide the training of neural networks, or developing hybrid architectures that combine the strengths of both approaches.
From my perspective, I'm fascinated by the potential of using neuroscientific insights to inform the design of AI algorithms. Studying how the human brain solves complex problems, especially during events like the Math Olympiad, could provide valuable clues for developing more intelligent machines. I'd love to see research that explores the neural correlates of mathematical reasoning and how we can translate those findings into AI models.
I think the key is to focus on developing algorithms that can seamlessly translate between different representations of information, spatial, temporal, symbolic. This could involve exploring new architectures that are explicitly designed to handle spatiotemporal reasoning, or developing new training methods that encourage models to learn more abstract and generalizable representations. The core thing, in this example, is the ability to translate from Cartesian, polar, and parametric.
Yeah, maybe even building in some kind of explicit representation of coordinate systems into the model itself. That's an interesting idea, Donald.
Thinking about it, how could we use these AI systems, even in their current state, to augment human problem-solving abilities? Could they be used as tools to help mathematicians and scientists explore new ideas and discover new proofs?
Absolutely. Even if they can't solve the problems themselves, they could be used to generate hypotheses, explore different solution paths, or even just provide a fresh perspective on the problem.
Yeah, I think that's a more realistic and potentially more fruitful application of AI in the short term. Using AI to assist human problem solvers rather than trying to replace them entirely.
I think one area is to use the AI to check for errors and inconsistencies in human proofs, or to help automate some of the more tedious aspects of mathematical research. Imagine a co-pilot for scientists to help them explore new ideas and accelerate the pace of discovery, especially translation between spatial representations.
It's interesting to think about the ethical implications as well. As these AI systems become more powerful, how do we ensure that they're used responsibly and that they don't perpetuate biases or create new forms of inequality, especially if they are used in cybersecurity?
That's a huge concern. We need to be very careful about how we train these models and what data we use to train them. We also need to develop methods for explaining their decisions and ensure.
I think it's also important to consider the potential for these systems to be used for malicious purposes. AI could be used to develop new weapons, spread misinformation, or even manipulate people's behavior. That's why it's so important to have a broad societal discussion about the ethical implications of AI and to develop appropriate regulations and safeguards.
Right, because that kind of manipulation is definitely something that could arise from the ability to translate between spatial representations. To think about how a human could be manipulated, you have to be able to translate how they perceive the world. So with that ability comes great power and, potentially, great evil.
It seems like we've barely scratched the surface of this topic. There's so much more to explore about the potential and the challenges of building truly intelligent machines. But I think this discussion has highlighted some of the key questions and some of the most promising research directions. What do you think would be the most impactful experiment in the next year?
I think the experiment that will settle the debate is to see how well some LMs do in the next USA Math Olympiad. What's the error? What strategies do they employ? That will be very interesting.
I want to know how well neuro-symbolic algorithms do. Let's create a competition between the two.
The biggest experiment is to see if AI can translate between polar, Cartesian, and parametric coordinate systems.
That's a great note to end on. Thank you all for joining me today for this fascinating conversation. And thank you to our listeners for tuning in to Cognitive Spirals. We'll be back next time with another deep dive into the world of consciousness, cognition, and machine intelligence.